Good afternoon. My name is Gemma Busquet. I'm a lecturer professor here at the department, working in the star formation group. And well, I did a PhD thesis here at the University of Barcelona about more than 10 years ago. And in September, I joined the department and the ICC, so I'm very happy to be here today and give you a flavor of my research. And I will first present you the group. We are a small group with Paolo, Belli, and Zuja. Zuja is finishing the PhD thesis, working on simulations in a star formation. And Robert, Rosario, and myself, that we work mainly in observations. So I will start explaining a bit of the scientific context of my research, mainly on the radio properties during the earliest stages of star formation and on the formation of high mass stars and stellar clusters. So stars form within molecular clouds that contain about 10 to the 5, 10 to the 6 solar masses of material, and they span several tens of parsecs. And these molecular clouds contain at the same time denser substructures that we call dense cores, that at some point these cores collapse, forming a protostar surrounded by an envelope of gas and dust material that falls into an accretion disk. And at the same time, the protostar drives powerful molecular outflows and jets. After a few million years, the envelope is dissipated, and we have the star and the disk system visible with a protoplanetary disk forming planets inside. And during the evolution, there is the complete cessation of the accretion onto the star, and the star enters the main sequence with the stellar and planetary system. And at the end of this life, and depending on the mass of the star and in the multiplicity, the star will replenish the interstellar medium with new material, which enriches the next generation of stars. So during all the process of star formation, protostars and young stellar objects emit at radio wavelengths from the deeply embedded class 0, class 1 protostars to more evolved pre-main sequence stars, or T Tauri stars. And this radio emission could be thermal emission, for instance, from thermal radio jets, or from the thermal dust emission from the accretion disk and the envelope, or could be non-thermal emission due to, for instance, gyrosynchrotron emission from very active stellar magnetospheres that is typically associated with T Tauri stars, or from synchrotron emission from the relativistic jets. The early stages of the star formation then involves a balance between the accretion of material and the ejection of material. And the mass assembly starts as an infall onto the star disk system from the parental envelope. You have to imagine here that there is an envelope and there is this inflow of material, and then this accretion proceeds from the disk onto the star. And due to the interaction of this accreted material with the stellar or the disk magnetic field, we don't know yet, it produces highly velocity and collimated jets that remove the angular momentum and allow the material to accrete onto the star. What we know about the accretion and the ejection is from this sample of low, intermediate, and high mass protostars and young stellar objects. There is a correlation between the mass accretion rate and the mass of the star, and shown here. Here it contains embedded objects from different masses and different luminosities, and as well as more evolved objects like T Tauri or Hedwig AEBE stars. And we can see that this correlation spans a large range of luminosities, which suggests that there is a common mechanism that controls the accretion of material for all the luminosities. I want to say here that the method to obtain these mass accretion rates is different depending on whether the object is deeply embedded, that we have to rely on indirect methods, or for pre-main sequence stars that can be inferred from optical lines. On the other hand, we know also that there is a correlation between the radioluminosity of radio jets and the volumetric luminosity, as shown here, that spans also a wide range of luminosities. And these radio observations are actually a powerful tool to investigate the connection between the mass accretion that is proved by the volumetric luminosity and the mass ejection that is proved by the thermal radio jets, by the radioluminosity. So we know that there are currently very few angularly resolved radio jets. Show here a table that was compiled by Guillem Anglada in 2018. This table has increased a little bit, but not too much. And these radio jets have a thermal origin, as shown here by the positive spectral index. And they are important because we can infer very crucial parameters like the injection opening angle, the injection radius, the mass loss rate, and these are important to understand the launching mechanism of the jets. But the jet interacts with the surrounding material and produces very strong shocks that emit over a wide range of wavelengths. Here in the image is the L1157 outflow. It's an infrared image from a Spitzer. And here it's a very bright shock. It's called B1 that emits in the optical, shown with the black contours, but also in the millimeter wavelengths with the white and the blue contours here. In this case, this is a radio jet from a massive star. This is the jet. And in the other panels, there is overplotted emission from the X-rays in red contours. So in this case, there is in the shocks from the jet, there is emission associated with that emitted at X-rays wavelengths. And in these shocks, most of them, they have non-thermal emission. They are associated with synchrotron emission from relativistic electrons, as shown here by the negative spectral index. This is the position of the central object that powers the jet, and the spectral index is positive. And these shocks are also very rich in molecular emission, molecular lines. For example, several deuterated species or even complex organic molecules have been detected in these shocks. On the other hand, regarding the accretion disk, these disks are accessible mainly through infrared and millimeter wavelengths. And here you can see that at the infrared, we prove mainly the upper layers of the disk, but very close to the protostar. But in the millimeter and submillimeter regime, we can prove the disk midplane, and so we can trace the material, the raw material and the cold material from the disk midplane where the planets form. So this is only accessible through millimeter wavelength observations. And this disk, because the star emits strongly in the X-rays and in the UV, then these X-rays and UV contributes to the photoevaporation of the disk. So in the centimeter, we can also prove these photoevaporated disks. So in the last decade, we have actually experienced a great progress in our understanding of the radio properties of young stellar objects and protostars, but mainly from the nearby regions. Here is an example of the different surveys that have been conducted in the Perseus, Taurus, Serpens, Ophiuchus, and in Orion. But all these regions, in exception of Orion, all these regions contain low mass objects, and they are not representative of the star-forming complexes in the Milky Way. And only in Orion there is one single very deep pointing that has been performed so far. We know that the most stars in the galaxy form in groups or in clusters rather than in isolation. So to form a cluster, there should be a high degree of the fragmentation from the molecular cloud that actually consists of different filaments. These filaments contain denser cores that fragment and form low mass stars and high mass stars at the same time. So these massive stars emit strongly in the UV and the X-rays. They power very energetic outflows and jets, and the stellar densities are high enough that it's possible to have dynamical interaction between the different cluster members. And all these ingredients may actually have important consequences for the formation of stars and for the formation also of a planetary system. So there are several open questions that I am interested in and that I am currently trying to address now and in the future, and regarding to the formation of stellar clusters. And this is mainly because most of the previous surveys were limited by the sensitivity, and this allowed only to detect the most massive objects, but not the complete cluster. And these are the questions that I would like to address: how the environment influences the formation of star clusters and the planetary systems, what determines the number of objects and the stellar densities, how mass accretion and mass loss rates evolve with the time, and if it's the same way across the entire mass spectrum, and whether the radio properties, infrared and X-ray properties of the cluster members are similar or comparable to those inferred in nearby regions that form mainly stars in isolation. So this is part of my present work, this is part of my future work, and I will now explain you a little bit of the, let's say, past current work that is part of a multi-wavelength, multi-scale observational campaign toward an infrared dark cloud that it's forming a cluster. And I will focus mainly on the fragmentation and on the stellar population of this cloud. So I will introduce you briefly the cloud. This is G14.2, and this cloud harbors a network of filaments that emanate from two different hubs. This is the north hub and the south hub. And the cloud is associated with a very rich population of protostars and young stellar objects that have been identified with Spitzer and Chandra. And from millimeter interferometric observations with SMA and ALMA, we know that the hubs harbor an embedded cluster, and that they present different levels of fragmentation, with the northern hub less fragmented than the southern hub. So this is to just show the different instrumentation that we were using to understand the formation of this complex network of filaments and why these hubs fragment differently, even that they share some physical properties that they have in common. So we conducted ALMA observations and very deep GBLA observations that I will show you right now, and then also a multi-wavelength campaign in polarimetric mode that was part of the PhD thesis of Nacho Oñez that finished last year. So here I'm showing a project that it's an ALMA, it's an ALMA observations. We did two very large mosaics trying to encompass the whole cloud, and the idea is to prove the kinematics of the gas. We have the contours here is the dense gas, but we want to study also the low density gas like using these tracers, the 13CO and the C18O transitions. You can see here the movie with the channel maps of the 13CO that shows really a complex structure you will see right now, which approaches the cloud velocity. So the idea is to prove the kinematics from low density, high density tracers, and then compare it with the simulations with different treatments of the turbulence, the gravity, and the magnetic field, and understand which of these ingredients is dominant or controlling the dynamics and the formation of these structures. And these are part of other ALMA observations. These are very, very sensitive observations. You probably don't see it very well. This is towards the north, and this is towards the south. In this case, we are interested in the compact emission, and we ran an algorithm to identify sources. This is the output from the algorithm that did a pretty good job in identifying sources. You can see that we can now detect a lot of more fragments that we knew previously. And in this case, both regions seems to have the same number of compact sources. So now we will explore, no, let's say whether this fragmentation could be consistent with genes fragmentation, with thermal fragmentation, what is the separation, how is the mass segregation in these two clusters, and so on. And finally, for this part, this is another pilot program that we did with the very large array with the most extended configuration at 2 different frequency bands. This is the cloud. We did a couple of pointings here that is not well seen. We detect about 80 sources. And because we want a very high sensitivity comparable to the surveys that were performed in nearby regions, the observing time is high. It's about 11 hours per pointing. So this is a pilot project. Because we know the stellar content from infrared and from the X-rays, we started to cross-correlate, no, the BLA sources with the other wavelengths. And I have to say here that the millimeter, it doesn't include the new ALMA data. This is from all data. And you can see these are the number of radio sources, whether they have an infrared counterpart, X-ray counterpart, or millimeter counterpart. And I have to say that there are additional sources detected in the infrared or in the X-rays that are not included here. So that there is an important, an important population that doesn't emit, or at least we cannot detect right now with our observations. So I will go faster. This is some examples of the kind of sources that we detected. Some are really very compact, others like a jet-like morphology. So we will explore the ionizing mechanism for these sources, whether they are radio jets or H2 regions. And I will finally end with the future work. First, I will give you a few sense of the current status of radio interferometers and the future, or the future for the radio astronomy. And then I will explain you a little bit on the BOLS project. That was a BLA large project that has been accepted recently. So regarding the radio facilities, we have ALMA that it has been operating for a decade with 8 out of the 10 receivers already installed. So these are the 2 remaining receivers. This is band 1 it's already under construction and will be installed soon. Band 2 is not yet constructed, but this will be important because there are a lot of molecular lines that emit strongly in this band, and with the advantage that it's less crowded than other atmospheric windows. And then for the SKA, of course, I'm interested in SKA mid, and because of the high angular resolution and the high sensitivity, it will be the perfect instrument to resolve radio jets, to do large surveys of different regions to study protoclusters. And with only 1 hour of observing time, you can reach the same sensitivity as we did with the 11 hours with the BLA. And then the NGBLA, that it's under design. And if it's funded, it will be an excellent complement to ALMA and the SK for the Northern Hemisphere. So I will finish with the BOLS project. This is the BLA Orion A large survey. This was a large project submitted last fall and accepted by the end of this year, and we have been awarded with 306 hours of observing time. This is a large collaboration with more than 40 researchers from all around the globe that are involved, and we are interested in mapping a significant fraction of the Orion A. This is the coverage of the BOLS. That includes the densest region of Orion with and also with the highest stellar density. It's here. We will observe this in two different frequencies, and including also some masers and radio recombination lines. So the idea is to understand or to study the connection between the mass accretion and the mass ejection using the radio observations and complement it with the Gaia data release catalog. So why Orion? There are several reasons for targeting Orion. I mean, Orion is the nearest cloud that harbors high mass stars. It's the largest cloud that contains low and intermediate mass stars in the solar neighborhood. It contains a wide range of environments. There are rich clusters, like in the Orion Nebula clusters, that emerge from massive filaments, and there is also a more scattered population in the low density regions. And finally, because it interacts with an OB association, also here in the Orion Nebula cluster. And here I show the coverage from different surveys, from Herschel, from Spitzer, and from the VISTA survey. So all of these near-infrared and far-infrared facilities have target Orion, have mapped all the Orion molecular clouds. So there is a lot of information like the stellar content, the spatial distribution. There is spectroscopic data with the stellar luminosities, masses, radii, ages. Also, it has been observed in the X-ray with Chandra and XMM Newton. And there is an inventory of the dense gas, of the filaments, of expanding shells, and so on. So there is a lot of ancillary data that is accessible to complement the BLA observations. And so this is the dots indicate the number of young stellar objects that were detected with the Vision survey. There are about 1,640 objects, with only 145 having a counterpart in the centimeter wavelengths. It has been observed with Herschel. This is the number. Here I show the number of sources and the number of in this survey, and the number of sources that have a radio counterpart. Has been observed with ALMA and the BLA at other wavelengths, and there are about 1,300 stars from the Gaia early data release catalog that have a counterpart in the Vision. And I finish here. So these are more or less the goals: obtain the census of the stellar population and build this radioluminosity function over different range of masses, luminosities, evolutionary stages. Look for correlations between the spectral indices and evolution. So we hope now that we can expand these kind of correlations, the radioluminosity of jets with the bolometric luminosity, and understand the connections and quantify the accretion and the mass lost. Of course, there are secondary goals that I leave here. I just want to let you know that if you are interested in doing ALMA observations, BLA observations, radio observations, and this is not your field, I will be very happy to help and provide support, technical support. Maybe the science is not my field, but I can provide support from the technical side. So just come to my office and or write me an email, and I will be very happy. And that's all. Thank you.
Thank you, Gemma. Okay, we have time for 1-2 quick questions. Okay.
Hi, I have a question regarding the jets of these protostellar objects. And well, you can have jets also in other objects like X-ray binaries, for instance, where they come from black holes or neutron stars. So what are the main observational differences between the jets of these protostellar objects and the ones that are produced in binaries?
Okay, well, it's not my field, the other in binaries, but I assume that mainly from a protostar, the emission is thermal emission, probably in a pulsar or whatever is non-thermal emission, is synchrotron emission. The velocities, are higher also. They are faster jets, and in this case, and more relativistic electrons. And I don't know if the mechanism should be similar, but I don't really know if it is exactly the same. I mean, there are a lot of similitudes, but and a few differences. I don't know, maybe you volunteers.
Well, basically, you can find many small differences, but the main difference is velocity. So
Velocity
speed
is
in
right.
microquasar, they are relativistic speeds for the flow, and in the case of
for a
low mass, high
protostar,
mass
it's a
protostars
few
would be several
hundred.
1,000 kilometers per second.
Exactly. For a protostar, it's a few hundred kilometers per second, usually the velocity, and from I think more than 1,000 or something like that. So they are faster.
Okay. Okay. Let's thank Gemma again, and the speakers of the first session of the afternoon. Let's reconvene in 25 minutes for the last session, which will be technological. So it's 4:20.